All right, so continuing dealing with forces, we're now getting into the big topic in statics class, and that is equilibrium. So today we're going to deal with particle equilibrium. So a particle essentially assumes that whatever object I'm dealing with is really, really small. So essentially just a point. If it is just a point, I don't have to worry about rotation. So this is equilibrium, not counting rotation. For now, we'll get to the rotating part in a few weeks, actually less than that. But equilibrium essentially means that my object has zero net force acting on it. So if we go back to Newton's second law, net force is mass times acceleration. If the net force is zero, that means the acceleration is zero. If the acceleration is zero, that means if it's already at rest, it's not going to move. If it's already moving at a constant velocity, it'll stay moving at a constant velocity. But again, that's not the one we care about. This being statics class, I only care about that at rest part. So if I have an object in equilibrium, net force is zero, it means it's going to stay not moving. And that's generally a good thing for the things we're dealing with. The bridges, buildings, we don't want them to move because moving means they're going to fall over. So equilibrium, specifically static equilibrium, is really what the point of statics class is. So anytime we're dealing with equilibrium in this class, we'll deal with the static version, so objects not moving, as opposed to the dynamic version, which you may see in dynamics class. So that brings us essentially to the big equation for this class. So another way to write the net force is the sum of all external forces acting on an object. So if you take all the forces, all the external forces, add them all up, if that equals zero, you're in equilibrium, and that's a good thing. So this, I kind of joke, is the big equation in this class that we spend the next 10 weeks solving the same equation over and over again. So by the end of this class, you may be sick of this equation, but we'll be using it a lot to solve a lot of statics problems. Since this is a vector equation, you can break it down into its three components. So I can have the sum of all the forces in the x direction equals zero, sum of all the forces in the y direction equals zero, and sum of all forces in the z direction all equals zero. So these three equations all need to be satisfied for static equilibrium to occur. Same thing as this one vector equation on top. Sometimes we're dealing with two-dimensional systems, so only forces in the x and y directions, in which case we only have to solve two equations. The third equation's kind of solved for by default based on the fact there is nothing going on in the z direction, so there is no force in the z direction, so that's automatically satisfied. So basically, two or three component equations to solve over and over again for the next few weeks. Now, before actually solving these problems, really good thing to do, especially in this class, it's going to help you out in later classes as well, is the first step when you solve problems should always be to draw a free body diagram. So a free body diagram is essentially a diagram of whatever single object you care about and all the forces acting on it. So again, for today, we're going to deal with a particle. Particle, I'm assuming, is fairly small, so it could essentially be represented by a point. Free body diagram for a particle is generally just a point with a bunch of arrows coming off it, indicating all the forces acting on it. But in general, when you draw free body diagrams, we're dealing with an extended object. So just keep it with extended objects for now. So even though I'm going to assume this box is a particle, I'll still draw him as a big box. Just gets me in that habit for when I do it later. So I have this box, I have a rope acting on this box, and I'm probably given some details about how much tension is being pulled on and other things to do with this box. But again, the first thing I want to do is my main concern is this box. So my free body diagram, I get rid of everything other than this box. So the only thing I have is a box. And then anything else acting on it has a potential to apply a force to it. So now I want to identify what forces are acting on this box. So I see I have a rope. This rope is probably pulling on it with some tension, some tensile force. So essentially, instead of having a rope here, I replace that rope by some tensile force T. So acting at that point, wherever the rope is attached, along the same line as the rope, as we saw last class for ropes and strings. They go along the same line as the rope itself. So whatever angle this rope made, that's the same direction as this tensile force from the rope. Other things that could be acting on this box, I have the floor here. So because I have the floor, I probably have some normal force. because this box is not going to fall to the floor. So there's some normal force acting on the bottom of the box, pushing upwards to hold it from moving to the floor. Other things that could possibly be acting on my box, obviously, I'm assuming I'm going to be on the surface of the Earth, so there's going to be some weight involved. So weight force, again, as we saw last class, right in the middle. I'm assuming this box is homogeneous, so weight goes right in the middle, if not center of mass. So weight force going down from the center of mass. And then possibly also I could have friction. This may be a rough surface, again, depending on the question. So I could have some frictional force, again, acting on the bottom of the box. I'm going to draw this guy to the left because, again, if I have a rope pulling to the right, friction is probably going to push to the left, because if this box is going to go anywhere, it's going to go to the right, which means that friction has to push to the left. So that's basic free body diagram. You just have the one single object you care about, and then take away everything else and add in all possible external forces acting on that object, like I did here. So more formally, what I just did there to construct my free body diagram, first thing I did was draw the outline shape. So just the box, that's the only thing I cared about. Drew the box, didn't draw anything else. Just got rid of the rope, got rid of the floor. So only care about that one object. And then show all the forces. So whatever force could possibly be acting on my box, I then drew that. Again, here only the external forces. So whatever external forces I had a normal force, tension force, gravity, and a frictional force. So I drew those where they belong, proper directions. So all the forces, they can be either active forces or reactive forces. So that just means active forces don't really depend on anything else going on. Gravity is always going to act. Doesn't matter whether there's other forces or not. Tension, if you're pulling on something, is always going to be a pull on something, whether there's other forces or not. So gravity, tension are my active forces in the previous case. Reactive forces are things like the normal force and the frictional force. So without gravity, there would be no normal force. So normal force depends on gravity being there. That's why it's a reactive force. Same thing for the frictional force. If I'm not pulling to the right, there's no reason to have any friction to the left. So the normal force and frictional forces are the reactive forces in that case. And then when I drew them, all my forces, I drew them at their proper locations with their, at least guess-wise, of their proper magnitude. So some rough indication of the length of the vector telling me the magnitude of those forces. So point of application, magnitudes, directions. If you know any of those things, make sure that that's drawn on there as well. If you don't know any of those things, that's fine too. So I kind of had to guess which way friction was going. I had a pretty good guess in the previous case, but some cases that may not be the case. In that case, just draw friction, whichever direction seems most reasonable. You may be right, you may be wrong, doesn't actually matter. If you're wrong, in the end, you'll just end up with a minus sign indicating the opposite direction, which is fine. Similarly, my normal force, I wasn't entirely sure where it was, but again, throughout my procedure and analysis, I should be able to solve for where that normal force actually occurs, and then have a better idea as to what it's actually doing. So speaking of analysis for the problem, generally the first thing you want to do is draw your free body diagram. So we just kind of went over how to do that. In addition to the free body diagram, you also want to establish your coordinate system. So usually standard coordinate system, X going positive to the right, Y going positive upwards. We'll be using that a lot, but that's not necessarily the only coordinate system you can use. You can use whatever coordinate system you want. So if you are using something that's a bit different than the normal ones, you want to make sure that that's on your free body diagram as well, so that you know which way things are going. And then, as mentioned in the previous slide, draw all your forces on your free body diagram. If you don't know anything about any force, point of application or magnitude or direction, you can kind of assume that on your free body diagram and solve for it later, which is basically part 2. And so the way you solve for anything is to use the equations of equilibrium. So sum of forces in the X, Y, and Z directions all add up to 0. So you basically have 3 equations for any scenario. basically that all the forces in each direction add up to 0. And from that, you can probably solve for either magnitudes or directions or things that you may be lacking on your free body diagram. And so if you're actually solving for example, friction in the previous case, and you drew friction in the wrong direction, you'll just end up with a negative magnitude. So again, negative magnitude means flipped 180 degrees. So a lot of times you can just guess which direction the force goes. If you're wrong, you just end up with a minus sign. No big deal, just means you guessed wrong. But by the end of the analysis, you just know that just means the opposite direction, and everything else still ends up being right. So that's the basic procedure for analysis that we'll be seeing a lot in this class. Again, this is specifically for particles, not dealing with rotation. In just over a week, we'll deal with the actual rotational version as well.